cross-sections, how they evolve with energy and so forth. If you want to add perturbative contributions, you have to add those separately if you want to describe jets or charm quarks, bottom quarks, things like that. And so I think I'm not too familiar with the models that are used in the cosmic ray community, but I think QGS jet starts from this limit here. On the other hand, there are the models that I'm more familiar with, and the modeling world that I come from, and this talk will focus mainly on these models that are anchored in perturbative QCD. So we really start from perturbative calculations, Feynman diagrams, scattering cross-sections in perturbative QCD. And then we rely on unitarity, which is, of course, a concept that goes beyond perturbation theory itself, and some infrared regularization of these very divergent cross-sections, which otherwise would just become infinite. And this then leads to the notion of multi-parton interactions. And you have these perturbative phenomena of parton showers, so radiative corrections, and then ultimately also models of hadronization. This divergent cross-section you then regulate at some low infrared regularization scale of order a few GeV, and you say that that's due to color screening. You cannot exchange colored quanta at wavelengths longer than some screening distance inside a hadron, or saturation is also related to that, and you get some sort of center of mass energy dependent value for this regularization scale, which is then the main sort of tuning parameter. This framework itself is a priori unpredictive for things like the total cross-section, all of these things here, single diffractive, double diffractive, and so forth. So you get your total cross-sections from Regge theory, for instance, Donaky-Lanzov parameterizations and so forth. So there is some interplay between these two different pictures. They are anchored in different limits, but they each, if you want to describe all of it, you need to borrow concepts from the other one. And exactly how you do that leads to differences between the models. There are also some models that I would call mixed, that really genuinely incorporate aspects of both languages. And here I've put EPOS and FOJET, and I'll leave it up to the authors of those tools to say whether they think that's justified. So the structure of an LHC proton-proton collision from this sort of perturbative QCD anchoring point of view is that you start with a hard interaction, you calculate a hard scattering cross-section, maybe you also have some resonance decays and so forth. Then you have an era of radiation, parton showers, Bremsstrahlung, these accelerated charges, they've been kicked around, they radiate, they give off Bremsstrahlung. And finally, then you have these multi-parton interactions that I was referring to before. So additional parton-parton interactions inside the hadron-hadron collisions, and you add beam remnants, so the remnants of the hadrons that you've extracted all these partons from. And then finally, so I wanted to say that these multi-parton interactions, these additional color exchanges, they are the equivalent of what you would call cut pomerons in the Regge theory. So they act to exchange color between the beam remnants, just like cut pomerons do, and you scatter additional color into the event. Finally, then you have strings in this language here of string confinement, string models of this confining field. There are lots of ambiguities to do with exactly how the strings form, how these color charges that are being scattered actually then translate into color singlet hadrons, how the strings form and how they decay into hadrons. And those are some of the things I'll touch on here. Okay, so let's go back to basics and talk about why string models to start with. The basic observation there is what we call linear confinement. So on the lattice, in as close to honest to God QCD as we can calculate, you can compute the potential energy of a quark and an antiquark in a color singlet state separated by some distance as a function of the distance. And you see this Coulomb part, 1 over r part at short distances, but then a linear part at long distances. And this linear term is then what gives rise to, or that linear term is interpreted as the equivalent of a string potential with a tension about 1 GeV per Fermi. So that term is what gives rise to phenomenological models that are based on strings, conventional strings, and that's also called the Lund model. In one slide, how these strings then evolve and fragment, this notion that color charges drag strings behind them provides a mapping. So quarks become endpoints of strings. Here are some time snapshots of a string system evolving from a quark, an antiquark, and a gluon. And gluons map to transverse kinks. You can see that there's a sort of a kink on the string that the gluon drags out. So you have a map up from the perturbative degrees of freedom to stringy degrees of freedom. And then you have basically the world sheet of a string that evolves in space-time. It's governed by classical string theory, how it will move. Then on top of this string world sheet surface, you postulate that there's a probability for string breaks to occur by quark-antiquark pair creation. And the analogy we make there is with what's called the Schwinger mechanism in quantum electrodynamics, where you can have E plus E minus pair creation in a strong electric field. So you can have QQ bar pair creation in a strong chromoelectric field here. And so this string will fragment by pair creation, and you see it breaks into little string pieces, each of which we then interpret as a hadronic state. So that's how we then map from quarks and gluons to strings, and finally from strings to hadrons. And one of the universal rules in this pair creation process is that the probability to pop a quark pair from the vacuum depends in this way here, in a Gaussian way, on the mass of that quark. So strange quarks are heavier than up and down quarks. And that means that the probability to get strange quarks is suppressed. So there's a smaller probability to get strange hadrons than to get pions and rhos and so forth. And so if kappa, this string tension, is a universal constant, and these quark masses are universal constants, then the strangeness suppression is a universal constant as well. And interestingly, data has shown very interesting discrepancies with this notion of jet universality that we then try to interpret what is causing what we call strangeness enhancement at the LHC, and we wonder whether that also has an impact on things like cosmic ray cascade properties. So I'll get back to that. I wanted to mention an alternative to the string model. So if you're doing collider physics, at least, we talk about string models of hadronization and cluster models as well. And Herwig and Sherpa, the other two big general purpose event generators, use what's called the cluster model. And so instead of modeling these quark-antiquark pair creation processes as string breaks, what they do instead is they take each of the perturbative gluons that you have at the end of the shower. So let's say this second black line is the end of the shower, and there's a gluon. In the string model, that would form a kink on a string, these two gluons here. But in the cluster model, you force these gluons to break into a little QQ bar pair. So you postulate that as a non-perturbative break. And then you get these little QQ bar clusters that are produced by these breaks. And there's a universal invariant mass distribution for them. So you can say that you have a hadronization model that is at least universal, that you can use for different center of mass energies. So I'm not going to dwell on the cluster model because I don't think it's used very much by any cosmic ray related codes, but I wanted to mention it, at least what the basics are. So in string fragmentation, as I mentioned, there have been a lot of new directions that are being pursued at the moment, some of which may be relevant to understanding properties of cosmic ray cascades. And increasingly, and again, mainly spurred on by these new discoveries at the LHC, we're starting to regard this tension in the string, so this 1 GeV per Fermi, the energy density in the confinement field, as an emergent quantity. These are not fundamental strings. They're not superstrings. We interpret them a little bit like vortex lines in a superconductor or something like that. Maybe for this community, cosmic strings is a better analogy, although these, of course, are much smaller. But they are dynamical quantities, and they can be, they arise, these strings, to enforce confinement when color charges are separated. And they could, in principle, this effective parameter kappa could, in principle, depend on a lot of things that you would not see directly in lattice studies. I don't know how much you know about lattice QCD, but it's mainly a tool for studying steady state, not time, so average steady-state quantities. It's not well suited for studying dynamical quantities. So it could depend, for instance, the effective string tension could depend on, let's say, the invariant time. You could think of strings that before they exist, they have to form. And maybe as they are forming, there's a Coulomb field, which doesn't look very much like a string field. And so at very early times, the effective string field is highly excited. You could think of that as a kind of a hot string that cools down with invariant time. And we did a small toy study of strings like that. You could also imagine that these strings, as they form, they have little excitations living on them. They might be a little lumpy, maybe pinched a little bit here, and they're a little bit wider somewhere else. There could be some dependence on the spatial coordinate of the string. And again, that's not something that has really been explored in conventional models. We're starting to explore that in a project I started with some colleagues here in Oxford. But what's really interesting for LHC data is whether it could depend on the environment. And that also becomes very relevant when we start talking about ion collisions, which of course play a big part in cosmic ray studies as well. Now, what I mean by the environment is whether there could be other strings nearby. And that is what this plot of cyclonic activity is supposed to illustrate, that I can have a cyclone and an anticyclone close by, and these things will interact. They're not independent. For the string model context, there are so far two main approaches to modeling environments of strings, non-trivial string interactions. One is called color ropes and has been pursued for a while. And another one that is maybe a simplified version of color ropes is we call close packing. And we have some work in progress on that. They are both designed to model how a big system of color charges would have confining potentials that are not independent of each other. So these strings could sort of squeeze each other or affect local changes on each other. So what is this environment in hadronic collisions? And you can also think of ion collisions if you want. So in hadron collisions, we're not hadronizing a simple string that is a quark stretched via a number of kinks to an antiquark. We have colored initial states. We have all the partons in the proton. We have gluon exchanges. We're exchanging color octets. So we have more complicated flows of color through these processes that we're looking at in hadron collisions. Also, of course, protons are composite. You have one proton, there's this whole beam of partons inside of it. And QCD partons really want to scatter off each other at low PT. We have this 1 over PT to the 4th scattering cross-section that I showed earlier. So there's this divergent parton-parton scattering cross-section. And even if we have a low angle scattering, if we scatter via gluon exchange, we're still exchanging color. So these low angle scatterings, they don't do much kinematically at the parton level, but they still exchange color. They scatter more color out of the beams. So this is just an illustration of the parton-parton cross-section, which diverges as you go to smaller and smaller PT. And at some point, it becomes larger than the total hadron-hadron cross-section. So we have this funny situation that the parton-parton cross-section is bigger than the hadron-hadron cross-section. And that crossing point, just in this case for 8 TeV proton-proton collisions, that happens at a perturbatively large scale. So 4 or 5 GeV is definitely a lot bigger than the confinement scale in QCD. And that's what gives rise to the notion of multiple perturbative parton-parton cross-sections. At a scale of 5 GeV, I should be able to calculate something perturbatively that has to do with the scattering processes that are happening. But I can also see that my parton-parton cross-section is saturating the total hadron-hadron cross-section. So how can I reconcile these two pictures? I can reconcile them if there are several parton-parton collisions per hadron-hadron collision. So my parton-parton event rate is counting parton-parton collisions, but if there are several of those for each hadron-hadron collision, then I can have this ratio be bigger than 1. So we interpret this ratio as the average number of parton-parton scatterings that I have at a given PT scale. And that's then what's used in these multiple parton interaction models. And the fact that this scale happens at around 4 or 5 GeV for these energies is why we think that there is something perturbatively calculable that we can do here, that we don't have to only use cut pomerons. So that's what leads to the notion of multiple parton interactions, which then give these additional color exchanges. So we really are scattering quite a lot of color. And again, these are sort of equivalent. They are finite PT equivalents of the color exchanges that we get from pomerons in a Regge theory approach, but they're calculated, they're arrived at in a slightly different way from a different limit. So, okay, we get these MPI or cut pomerons, depending on where your model starts from. Whatever you start from, you get lots of colored partons scattered into the final state. All of these partons then have, not all of them, but some of them have significant overlaps in phase space. They're going out at low angles, and so you have all of these partons that are sort of jostling around in phase space. And now you need to construct the confinement potential for this very complicated system of lots of colored charges. So, you've got red, green, and blue charges going all over the place. Who gets confined with whom? That's not a simple question. So if you just look, if you say the limit that there are so many partons that effectively each one is sort of random in color space, and you've got a triplet somewhere, you've got an anti-triplet, well, the random chance, if they weren't color correlated at all, the random chance that they would be in a singlet state so that they could confine is 1 in 9. And you can also say if you've got a quark and a gluon, there are some random probabilities for how they are correlated and so forth. And if you've got a lot of charges, so this is what we call color reconnections, when you allow random charges to sort of just connect with each other. That's often, or that's one word or one way that the word color reconnections is used, that you allow stochastic connections between partons that a priori shouldn't be color connected. So when you have many color exchanges, each one, the probability for you to reconnect with a given parton may only be 10%. But if you've got a lot of 10% probabilities, then ultimately it becomes more likely to reconnect with something close to you than not to do so. So color reconnections in dense environments become more likely than not. These, I think, are related to coalescence models. So if you have all these scatterings and partons coming out, then effectively what you've done is you've created a kind of medium for yourself. The medium is just made of all of these partons that you've scattered out. There's no medium in a quark-gluon plasma kind of sense. There's just a lot of partons going out in phase space. But the fact that you can sort of randomly pick up partons from that group of partons that you've scattered starts to look a little bit like coalescence models. So again, I think there are similar phenomena that are happening in color reconnection models that are happening in coalescence models, and we're talking about them in 2 slightly different ways, coming at it from 2 slightly different angles, but ultimately it's similar physics that we're talking about. I wanted to also mention baryon number. Could you get baryon number out of these color space ambiguities? And we think you can. So you may know that in string theory, you talk about open strings and closed strings. So open strings is like the ones I've talked about, a quark in one end, an anti-quark in the other, maybe via a number of kinks. And the probability for a random quark and a random anti-quark to be in a confining state is 1/9, as we talked about. Gluons create, so if I've got a pure glue system that's confining, those are octets. Sorry, I shouldn't have put a bar over the 8 there. That doesn't mean anything. I just copied and pasted from the 3 bar. But the probability, the random probability for 2 octets to be in a singlet state is 1/64. So it's not that big, but you can still have correlated gluons. But you can also have in an SU3, in a non-abelian gauge theory, you can have these things called string junctions. And they are also studied in sort of fundamental string theory, but here, of course, we're still talking about them in QCD. So you could have a red, green, and a blue set of charges that randomly are going in the same direction in phase space, and they confine together. They realize that they could form a baryonic state. If you do that, then there will be an anti-blue, anti-green, and an anti-red charge left over somewhere else. And so you're not violating total baryon number conservation by doing this. There will be an anti-baryon formed somewhere else as well, but this is just depicting that this is where the baryon forms. And could we be seeing these kinds of color accidents that create baryons at the LHC? And in fact, we think we do. So some years ago, we built a model, a simple toy model for allowing these kinds of color recombinations, reconnections in color space. And so you could have this situation where you had some charges that would reconfigure into baryonic. So you would create suddenly an extra source of baryon number that's only there when you have so many color charges that they start to want to do this, that the probability for doing that starts to become appreciable. And it was a great surprise and a nice validation to us to see these measurements of baryon to meson ratios from the LHC. Here's a charm quark lambda C divided by D, so baryon to meson ratio, which at low PT is sort of a factor 10 enhanced. So this is the rate, the cyan line here is the measurement that is consistent, or the modeling that's consistent with LEP, which does not have this mechanism enabled. And then when you enable the mechanism, you get the purple curves, which sort of go straight through the data, which is really impressive. There's a factor 10 enhancement in the baryon to meson rates. You see also on this part, so that was nice. These are these color reconnections beyond leading color. That's what we called the model. There are also some other models on here which also are able to describe the data. I'm only mostly familiar with the Catania one, which indeed is one of these coalescence type models where you pick up quarks from something that you call the medium. You don't really say where they come from the medium, but you have similar rules as to whether you can create baryons from picking up a red and a green when you've got a blue quark and so forth. So again, similar kind of physics, although it relies on the presence of a medium. So, yep. Okay. So I think that these that certainly we see these enhancements in baryon rates at the LHC, and we see that we are scattering this huge amount of color into the final state. So I need to speed up a little bit, I think. This is the multiplicity, the number of tracks that you have in the collision on the x-axis. And what you see here are different color representations. So how much flux are you scattering into the event, measured by the number of flux lines crossing the central rapidity, so the middle of the collision. And you see that as you get up into busy collisions, you're scattering lots of color. You get these very high representations where the conventional string that we have studied for decades is the color triplet, the fundamental string. But you see that at LHC, you access all of these higher representations. And so maybe what you're actually getting is a lot of strings around. And so one idea for what is driving what we observe as strangeness enhancement in PP collisions could be that tension is scaling up faster than it would if these were independent, but that they really are interacting systems and they have higher color charges. And that would mean that you would get more strangeness. So I will speed up and not talk so much about close packing, but we have some modeling of this strangeness enhancement that we are working on. And one of the big questions that we ask ourselves is these models that in various ways try to describe LHC measurements of strangeness enhancement, so more strangeness being created. If you get more kaons, you can get more muons. And so is there an impact from strangeness enhancement on muon rates in air showers? That's, I think, still an interesting question and maybe one that will be discussed at the conference. I also wanted to mention that what I have talked about so far is just string-based models, and without an actual hydrodynamical component to it, without a quark-gluon plasma. Now, that's one limit, a dilute limit, one can say, of the modeling attempts one can make. I think the most realistic, complete approach that we have at the moment for the full transition from proton-proton to proton-ion to ion-ion could be this core corona picture that Klaus Werner proposed in 2007 and has been working on with collaborators since, where you mix a string-based picture, so much like the one that I've described, for low multiplicity collisions and proton-proton, with a quark-gluon hydrodynamic thermal model for the dense parts of a collision system. So you have this division into a core and a corona of the collisions, and you interpolate between a dilute limit and a dense limit. And this is able to agree with lots of data that has been measured. I think there was at some point at least a too steep rise with multiplicity, but these are things that we are learning from, of course. I think it's quite an appealing picture, and I think there will be talks about this picture at the conference. There is a thorny issue with all of these models that it's challenging to describe the proton to pion ratio. And that's a bit of a thorny issue because, of course, protons and pions are the most abundant of all the particle species. So if we cannot describe the proton to pion ratio, then something is wrong with the model. And the problem is that, in fact, the LHC measurements indicate that the proton to pion ratio is a little bit smaller than what we see in E plus E minus collisions. And when we build models that increase strangeness, we tend to increase the rates of all heavy particles, including baryons, protons. So the proton rates also tend to increase. And that is not what we see in the data. So there are some challenges. Right now, I would think that's the main challenge for strangeness enhancement models. Can they describe the proton to pion ratio as well? And so there are ideas out there. I will not go into them. Do I have a minute or two?
Yes, of course, please.
Okay. Then I wanted to make connections with forward physics. So that's for us, that is beam remnant fragmentation. For a lot of years, of course, the beam remnant can be perceived of as a sort of a junkyard where you put the energy and the quarks and gluons that you got left over, and you send them down the beam pipe and nobody observes them. But that's increasingly not true. There are forward experiments at the LHC that are focusing on this region. And there are overlaps with interesting physics programs such as PHASA, the Forward Physics Facility, and of course cosmic ray fragmentation. There you are also interested in the bulk of the fragmentation, which is the forward scattering. And so some of these experiments that have been made at the LHC in the forward region, like LHCF, here's a plot here of I think this is photons, so photons mainly from pi0 decays of photon rates. You see some of these models that we use compared, so the energy spectrum compared to measurements from the LHCF. And what you see here is, for instance, that you can see the Pythia modeling here is too hard. There are too many photons with very high energies. And that's no good if you want to use this as a model for forward physics or to model photon production in proton collisions. So for us, of course, that means that we think that we are putting too many hard pions in our beam remnant. And likewise, one could measure that the neutrons, so the baryon part of the beam remnant, are too soft. So there's a division there between mesons and baryons, which is not right in our modeling of the beam remnant. So what to do about that? There are various ways that you can try and do something about that in your beam remnant, your division between quarks and diquarks, so double quarks in the beam remnant. The double quarks are what's going to give you baryons. You could say that this diquark carries a larger X fraction. That helps a little bit. And you can also veto that the baryon sort of spits off a meson that's harder than itself. So in the fragmentation process, when you fragment a diquark endpoint, there is a possibility that you sort of break up the diquark and fragment into that the hardest fragment becomes a meson, and the next to hardest is the baryon. So you can veto that probability if you say that, no, actually the diquark must become a leading baryon, and it will not break up. It will stay together, and it will form a baryon. And so playing tricks like that in the modeling of the beam remnant, this was not something that we had seen so clearly before, but the LHCF data really showed it. And then the phaser people really cared about it, and they showed that Pythia didn't work so well for that. And then we can play with the form of the fragmentation function and see if we can make it just right for their measurements. And you can get big improvements in describing these forward pion and neutron spectra. So the baryon and the meson component, and again, the pi zero will then become photons. It doesn't become perfect, but there is a new forward tune, a new forward modeling, which you can look up in this paper here. And that's the best that Pythia is currently able to do for this beam remnant fragmentation. There's then also the application of Pythia to cosmic ray air showers. That required more work. And so that is described by papers with by Torbjörn Sjöstrand and a previous student, Majos Utheim, in a couple of papers. And so that requires really modeling the whole array of possible interactions, including low energy interactions, which Pythia had not previously. We focused on high energy perturbative physics, right? So it has been extended with low energy hadron-hadron collisions as well, and hadron to proton neutron collisions at arbitrarily high energies as well. So that then needed to be extended to also handle things like proton oxygen, proton nitrogen collisions, to model collisions in air. And from that, we borrow basically the Glauber model from what's called Angantyr in Pythia. So just modeling the geometric overlaps, so that now we have a very simple model for hadron nucleus. There's still no quark-gluon plasma or anything like that, but at least you have a simple model that can do oxygen and nitrogen collisions, even if it's with simplified physics. Pythia, of course, is native C++, and that means you can do multi-threading, and you can do a simple interface with something like Corsica 8, which is how this interface was developed. So far, I don't think it has been put through all of its paces, but there is a model there which I think is interesting to look at. A couple of comments about it. If you look at these curves here, inelastic cross sections, here are proton, and pion-proton. Over here, it's the same thing for oxygen. Pythia are the red curves, and you see compared to some of these other models here. And one of the interesting things you can see here is that Pythia has the smallest proton-pion cross-section, but it has the biggest pion-oxygen cross-section. So that should mean that Pythia has qualitatively different behavior than you would get from some of these other models, and could at least be useful perhaps in exploring uncertainties. And then, as I mentioned, here is the simple extension to proton-ion collisions, where you just look at how many, this NCOL, the number of collisions, where you get this from the nuclear geometry, from a simple nuclear overlap model. So it's a simple model of proton-ion collisions, not at the level of sophistication of, for instance, EPOS, which has this more thermal modeling. And you can see that there are some differences in the cascades. I'll round up. Again, this is described in the papers that I referred to, but I just wanted to show you that they sort of peak at different values and with different magnitudes. The electromagnetic cascades are not so different, but the hadronic ones are, and you get different sort of trajectories of muons and so forth. Now, as I mentioned, Pythia is anchored in perturbation theory, so it natively includes charm and bottom and jet production. So those aspects are certainly there. And again, charm and bottom could have to do with things like muon production. It's native C++, which is a technical benefit in some contexts. And of course, with Pythia being sort of open to people to play with themselves, you can do user-level tunings and study interplay between observables that are relevant for air showers and accelerator constraints and so forth, where Pythia, of course, has been tested a lot. So that's all I had to say, and thank you.
Yeah, thank you, Peter, for this really wonderful review, which was really nice to listen to. Surely there are questions. Yeah, Sergey, not surprising. Sergei Ostapchenko.
Okay, thank you, Peter. It is indeed a very nice overview, but I have a couple of remarks, mostly on the points which require some improvements. First of all, a low PT cutoff. It's a bit, what one really needs is some mechanism. And the main problem is having the same parameter for regardless the centrality of the collision is dangerous. You know, you typically overestimate the effect in peripheral collisions like large B, underestimate. You average between two things. So dynamical mechanism would be really important. And second thing, in relation to that, it's very important to use constraints from structure function measurements. Because after all, it doesn't matter if you see parton cascades coming from the proton or coming from the photon. You have the same physics. Mm-hmm. And you know, Q-squared evolution of structure functions is well described by Diglebs. It's really the strongest limitation on any mechanism you assume for this low PT cutoff. Colored glass people come out of this, plugging in typically leading order BFKL and overcompensating by their, so to say, saturation. We don't have this freedom. We have standard Digleb. We may allow only a small modification of the thing. So that's my first comment. Okay, my second comment is about forward pi zero and neutron production compared to LHCF. Just a warning, playing with the remnant, a breakup and organization may be not a correct way. There you have quite a significant contribution from pion exchange. And in relation to PISA, unless I'm mistaken, it does contain pion exchange contribution, but only for proton production. It's in fact a part of the MX distribution for proton diffraction, the low MX part. But it doesn't have one for neutron production. And you know, in pion exchange, you produce neutrons twice more abundantly than protons. Okay, and the last comment is about the cross-section. The last slide you showed regarding cosmic rays. Well, it's a bit surprising. You see, you overestimate proton-oxygen cross-section at fixed target energies by 30% compared to experimental data. And no wonder. The Glauber model is 68 years old, and so far nobody wasn't happy with it. When you do this formula from number of collisions, you see number of collisions is dominated by central, mostly by low impact parameters, whereas hadronic cross-sections are dominated by the periphery. The beauty of the Glauber model, you have the amplitude, you get your total, you get your elastic, you subtract, you get your inelastic. You don't have to play with these things, which is highly model dependent, highly assumptions dependent, and so on. Moreover, I think I checked that it even violates unitarity if you plug it like this. Last comment, pion proton. Assuming 2/3, using additive quark model is fine at fixed target energies. But if you move higher in energy, you have parton diffusion. In Gribov's definition, at rank and Saylor walk. Your parton clouds get wider and wider. So once you come to sufficiently high energies, you don't care if you had 2 or 3 valence quarks. You have overall gluon cloud, which is much bigger than the initial valence quark configuration itself. So there is no reason at all that 2/3 should remain with increasing energy. I am done. Thank you.
Thank you, Sergei. So Peter, I don't know whether you remember everything, but
yeah, no, I think they are all valid points. This is still a very simple model. We would like to make it more sophisticated. It's the first extension of Pythia, well, towards cosmic ray air showers at least. There is a more sophisticated modeling of proton-ion collisions, which is this Angantyr, but the prospects for applying the full Angantyr machinery to cosmic ray collisions is still, it looks further in the future. So this is a very simplified framework that is available for the time being, with some simplifying assumptions.
There's actually, or you have more to say before, because there's another comment to that by Chloé Godus, who is working on Angetir and Pythia.
So hi, on Wednesday morning, I will give a talk where I have updated versions of this very plot you're showing right now, looking at this cross-section.
Oh, great.
And using therefore this Pythia 8.312 and using Angetir to plot these cross-sections. And so for the Pine proton, perhaps if I can comment now, the line will land in the highest energy between EPOS LHC and the current Pythia red line you have. So we don't have that much of an increase compared to the this.
Okay, great. That's perfect.
So tune in on Wednesday.
Yep.
An advertisement. So yeah, I think, Peter, I don't know whether you finished with replying to Sergey. What I would like to say, we have a discussion session on Wednesday. I think this is surely a topic where we can talk more about in the discussion. And I don't know whether there's a chance to participate in that, Peter.
I'm not sure either. I will be in an airplane on my way to Melbourne for the next, like, I don't know, 30 hours.
Not the best place. But
I will try and have a look and see whether I can. There were more things in Sergey's comments that I wanted to comment back on. Some of the comments about the first comments about saturation and this infrared regularization scale. Those I would really love to do more about that. It does feel like a very primitive thing to do, this PT0 regularization scale that we do, and make it constant. We have some slightly more sophisticated thoughts than that, but it has always seemed to me to be unsatisfactory that it's not really tied into the actual physics of saturation. And that would be a very nice development, to have a more dedicated way of treating that. What we get is a poor man's model of saturation, where effectively we have the parton densities that we use, the ordinary parton densities, which have some low X rise of the gluon. And they of course differ very much in how much their low X gluon rises. Different PDF sets differ enormously. And then we fold that with this PT0 cutoff, and the combination of those two things give you a turning off of your cross section, and that is certainly primitive. What you get is you get an effective cross section out that gives you basically an average number of multi-parton interactions, and that is what you are really sensitive to in most of the experimental constraints that we look at. But then things like the balance between forward and central physics is not necessarily described well from that. So I would like personally to understand better how to tie this PDF times PT0 regularization, to tie that better to saturation physics or saturation arguments, maybe along the lines you suggested. That sounds good.
No, definitely. I think we will, in the next couple of years, we will work more in that direction. And as Pythia is also entering into the game of the hadronic interaction models used for cosmic rays and for the tuning, I think we really discuss it more in the future. Okay, is there any other question here in the Zoom room? No? Okay. So then I think, so thanks again, Peter, for being with us.
Yep, thanks.
And I think, Eduardo, we have some announcement, right?
Yes. Okay. Thank you, Carl. Two quick announcements. First, this is a Mexican candy called mazapan. Please, there is a mazapan for every one of you. So, you know, it's peanut candy. So you need to open carefully and enjoy it. And please take this mazapan for you. It's a gift of the local organizing committee for all of you. So please take the mazapan. It's not is eatable. So enjoy. And the second is that thank you very much for all people online. Let's